So let's get started reviewing this 2025 edition of the AP Chemistry FRQ. My work here is not endorsed by the College Board. I don't work for them. I don't represent them. It's just my own representations and my own solutions. We'll see how well they are and how they stack up with the College Boards when they're released down the road. Another piece of information here, I am here to teach students through these problems as if this was a worksheet, not just a quick way to give the answers and see how well you did on the AP. I like to use these questions for the future. So understand, if I go a little farther than other people, it's because I'm trying to teach as well, and as well as give the answers. Okay, so let's continue and let's be crazy and start with number one. So number one, what we have here is an incomplete mass spectrum. And you can see my solutions here when they wanted you to fill in what the relative abundance would be for the other isotopes for magnesium. This is what this is about. Mass spectroscopy is measuring the relative abundances of all the different types of forms of the same element, and they differ by their neutrons, right? They're the same element because of the proton number. So we have magnesium here, and we can see that's got a big spike here, close to 80% abundance. So we should understand in this concept that the relative atomic mass should be closer to 24 because it weights, or it's weighted more to the 24. 80% of all the magnesium is 24, so should the weighted average. And that's what this is. But in any case, the problem's a little bit different. And so let's get there. So the percent abundance of magnesium is 24 is 79%. They want you to figure out the approximate relative abundances of 25 and 26. Okay, and so what they did, kind of cute, they said that the percent abundance of the other two natural isotopes of magnesium, 25 and 26, are approximately equal. So if we know it's 79% magnesium 24, then what we can do very simply, okay, is subtract from 79. That's what I have here, and I've got my 21%. Okay, and then I divide it by 2 because they have about the same. They said they are approximately equal in terms of their percentages in nature. So I divided by 2, and then therefore each magnesium 25 and 26 should be 10.5% respectively. Should add up to 100%. And that's why I carefully put this bar here, and each one of these is just a little bit above 10. That's 20, this is 10. Okay, so a little bit above that to give my 10.5 there for each of them to get the point. All right, so that's that first question. Very cute because I haven't seen that before, but not very difficult. But again, the idea is behind the weighted average. Okay, so we're on 1I, now we're in 1II, and now they want to describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and magnesium 26. This should be an easy question. These are isotopes, same element, therefore the same atomic number, but you notice the different number associated is the mass. And we should recognize this atomic mass, okay, is different between the two isotopes. The atomic number, which is the proton number here, is the same. To get neutrons, you can subtract the mass of the atomic mass from the atomic number, or the atomic number from the atomic mass, and get your number of neutrons here. If you didn't quite know that, they weren't asking for exact number of neutrons, just kind of going over it a little more than I have to, but you should recognize that magnesium 26 has one more neutron than magnesium 25, and you know the basics here are that a neutron and a proton represent all of the mass of an atom. The electrons have an insignificant amount of mass. They're 2,000 times lighter. So the entire mass of an atom is the nucleons, the protons, and the neutrons that are in the nucleus. Okay, but they are approximately the same mass, not quite. So if you take that for an account and you subtract, if the mass number is the proton and neutron, right, then This is the proton number. When you subtract, you get your neutrons. Any case, you recognize that magnesium 26 has one more neutron. Some very easy basics. So you don't expect these kind of questions on an AP. So, and again, I will say that this FRQ is in line with the post-COVID FRQs that are definitely have been easier than the pre-COVID for sure. So any case, moving on to the next question. So we start in B, and they give us a little particulate diagram of a magnesium ion being surrounded by water molecules and some solvation here. And they're preparing a solution of magnesium nitrate and, of course, a solution of sodium in two different beakers. Okay, fine. All right. Any case, the question comes down to a basic Coulomb's law. All right. And they say that a sodium ion in beaker has weaker attractions to water than magnesium. They're coming up and just saying that, okay? That you don't have to figure that out, but you have to support it using Coulomb's law. And if you notice, what they're doing is they give you two, okay, ways to describe that. Well, my friends, in chemistry, you should recognize the fact that Coulomb's law is based upon, all right, it's based upon the idea that we have the size of the charge, which is the Q's, and then the distance that charge has to travel to get to the other negative. Those are the two factors, and that's why they break it apart. I know some people were like, why is there two parts to it? Well, there's two parts to Coulomb's law. So in any case, the relative charge of the ions. Okay, well, the reason sodium has a weaker attraction to water than magnesium, its charge is smaller, right? In the what? Denominator of Coulomb's law, which, by the way, again, is the force of attraction. If the size of one of the charges, in this case the positive ion, is smaller, well, it's going to decrease the force of attraction to negatives. So what we're saying is when you compare the smaller charge of sodium +1 to magnesium +2, it makes sense that the force of attraction between it and the same ions would be less. And that's when you talk about Coulomb's law, it's the size of the charge over the distance squared. Okay, there's two factors. So I said the sodium plus has a smaller positive charge than magnesium +2. That's the force of attraction between the sodium and the partial charges. Okay, partial negative of the oxygen in water that is smaller than magnesium +2. So not sure if my wording is correct, but the bottom line is I'm telling more than I have to. It's about essentially, very simply, the size of the charge is less. That's really what you needed there. Okay, you didn't need all these extras I'm giving here because I'm just trying to teach through it. And then BII, what's the other part? Well, it's this radius or this distance. And we should recognize the fact that sodium plus, okay, is going to be a larger ionic radius than magnesium plus. And you may say, well, how do I know that? I know that sodium and sodium and magnesium, are next to each other. Okay, that's true. So sodium, magnesium on row 3, but sodium plus and magnesium +2 are actually isoelectric, right? So they have the same number of electrons, and therefore the one with the greater number of protons, okay, which would be magnesium, atomic number 12, is going to be smaller. Any case, so the idea very simply is that sodium plus has weaker attractive forces, the second part of this, because not so much that we're talking about the positive charge here, we're talking about the idea that it's a bigger ion. So that charge has to travel a longer distance to get to the negative. And the farther you are from negatives, hey, the force of attraction is less. And that's why I have the denominator here becoming bigger. That's for sodium. And the force of attraction has to be less mathematically. All right, so that's the second part. The distance is greater in sodium. In this question, you had to figure out that sodium ions certainly were larger. They didn't expect you to explain like I did, but again, I'm just using this opportunity to teach that. All right, on to the next part here, which again is how these questions are now being put together. They're kind of like going from 0 to 60 very quickly in different areas. So we're talking about Coulomb's law of ions attracting water when they dissolve, and now in C they want the pH of the solution in beaker B. So in beaker B, we should recognize very simply we've got ourselves a strong base. All right, anytime you've got a group 1 ion with a hydroxide or and some group 2 ions, calcium, barium, and strontium, even though they have to be a lower concentration, you've got complete dissociation. In this case, we've got a very low concentration, but we can expect complete dissociation of sodium. So we've got ourselves a strong base, and they want the pH. So because I know that all of the hydroxides can completely dissociate here, then I know the concentration of the NaOH is actually going to be the same concentration as the sodium, the hydroxide ion, which is the part that acts as a base. The sodium ion, of course, is going to spectate. Now, to get the pH, okay, what I'm going to do is I'm going to take and figure out the negative log. I'm going to pick this entire number and stuff it into a positive exponent. We're going to call that a POH. Little p means negative log. And I get 3.55. And a little trick that you should recognize is that the pKw, which is 14, minus the POH is the pH here. So you get a pH of 10.45, okay? And that's, to me, the best way to go from hydroxides into a pH. Remember, the pH is the negative log of the H plus ion concentration. All right, so yeah, nice, easy way. You got the hydroxide concentration, stuff it into a POH, which you recognize that this is really an exponent base 10. We should also recognize that we're going to subtract that from 14 to get the pH. All right. Any case, on to D. So D is showing us pouring these solutions together into one beaker. And in this question, we're combining these two solutions. And what they want to do is they want you to calculate the concentration of the magnesium. Okay, brackets means the molarity after the two solutions are combined. All right, so if you sniff this one out, this is the dilution formula. Now, I know some people use this for acid-base chemistry, and I'm opposed to it. This is where you use MV equals MV. Now, you don't have to use it. You can just get the moles, right? And then divide by the new total volume. I don't care how you do it, but really MV equals MV is the dilution formula, where you're going to take something that is more concentrated, and we're going to find, in this case, the new molarity after we pour its own volume into another volume, where now I have a total volume. So the molarity of the initial amount of magnesium ions, or in this case magnesium nitrate, but we should know that for every one magnesium nitrate formula there is one magnesium. So that's important just to recognize that. And then of course we're going to multiply that by its volume. So this is just, again, its initial molarity, its initial volume, and we're going to solve for its new volume when the volume is expanded. Okay, and why would it be expanded? Well, you're pouring two solutions together, so now, yeah, the volume, you have to add the two solutions together. So in any case, in this case, we had 35 milliliters, and we're going to add that to 50, and yes, we're going to have a total of 85. We're going to solve for that molarity, and that molarity should drop, right? Because you're going to spread that magnesium over a greater volume, so it's going to be less concentrated. And very simple, I think. All right, and that's something you should recognize and be able to do. So on to number E. So the dissolution, or the dissolving of magnesium hydroxide, is represented by the following equation. All right, so as you can see, it's a Q versus K question if you did not already recognize this. First point is, hey, write the KSP. The KSP is just an equilibrium expression. It doesn't have to be KSP. It could be KP. It could be Ka, Kb. There's many different equilibrium names that we give for different reactions. In any case, we call this the solubility product when ions, okay, break apart when a solid dissolves into its ions. In this case, very little, because the equilibrium constant is so small, so you don't have a lot of products favored. But in any case, to do the expression, it's products over reactants, coefficients become exponents, and solids and liquids do not apply. So you should not have a solid in your denominator. right? Solids and liquids do not apply. Products over reactants. Coefficients become exponent. We need a square there, okay? Any case, that should be a freebie. This is, I call low-hanging fruit. You got to really be able to pick that and get that point there. All right, so that's EII, okay? Felt like I'm a sailor here. But in any case, after the two solutions are combined, as described in part D, before any reaction takes place, the hydroxide concentration is 1.6 times 10 to the negative 4. Now, we haven't reached equilibrium. We just kind of poured them together. So this is like the instantaneous amount of hydroxide that exists. Using your answer to part D, which is where we did the MV equals MV, this is the value that we got right there. Okay, they want you to calculate the value of the reaction quotient. What's the reaction quotient? Well, it's the same formula as an equilibrium constant, but you're not at equilibrium yet. You're some position that is away from equilibrium. Either the Q has more reactants and less products in equilibrium, or it has too many products and less reactants as compared to equilibrium. You talk about those are the positions of the reaction quotient. That is a snapshot in time that shows the concentrations of reactants and products when they're not at equilibrium, which means they're working toward it, okay? In any case, to solve for them, we need values that are not at equilibrium. This right here that we solved for in D was the concentration of the magnesium instantaneously when they poured them together before any reaction occurred. And they just told you this for hydroxide. And by the way, where'd they come up with that? Well, they did MV equals MV for the hydroxide ion in the same way that magnesium did. Okay, any case, I'm going to put that in here. All right, and then some people will say, well, why not I just multiplying this by 2? Why isn't this number not times by 2? And people recognize that these could be stoichiometric values here. They never are for a Q, or it's almost very rarely, I should say, because this isn't something breaking apart into a certain ratio. This is just the values that we're pouring together. So that's the reason why. Any case, I put the big squared here because people forget that. Any case you do your math, I get my value of Q, which is some position that's not at equilibrium. All right, in this case KSP, which we can use to help to see how the reaction's going to change and move. Okay, and that's what I, Captain, is about. Told you, it's like being a sailor. This sailor, these questions. Any case. So using the reaction quotient Q, predict whether a precipitate should form. Don't forget in that KSP reactions, they write the solid and the ions this way. So the solid is first and the ions associate. Notice the double arrow. We're at equilibrium. All right. We already have a value for the KSP. That KSP was given to us, okay, in the top of the problem. So we're going to take our Q and compare it. And we can see that 2.07 times 10 to the negative 12 is bigger than 5.61 times 10 to the, 2.07 times 10 to the negative 11, okay, is bigger than 5.61 times 10 to the negative 12. So I know that the Q is greater than K. Okay, and right away, if the Q is greater than the K, and this we call it KSP for this type of reaction, a precipitate will form. The ions are going to come together more and move in a way that favors less of the products and more of the reactants. Okay, and if I think about it, why? In this question, you're only going to need to know that Q is greater than K, therefore precipitate will form. But again, trying to teach a little bit, I like to use this U diagram and hope you understand it. This represents 100% of the reactants, 100% of the products. Here is the value of, or the position of a theoretical KSP. It would never be 50%, I'm putting it there. But if the Q is greater, what does that mean? There is more products and what? Less reactants. I'm going to be in this position ahead of KSP. So what's it going to do? It's going to move toward equilibrium, and it's going to move in a pathway that's going to lower its products and increase its reactants. Okay, so that's what this is talking about. All right, and in fact, Le Chatelier's principle works the same way, except the problem with stating Le Chatelier's principle here is that we're not at equilibrium. So this is a classic Q versus K question. Okay, and again, word for word, Q is greater than K. You notice I have it in front. Therefore, we're going to work always toward equilibrium. That means that arrow is working in reverse. And a precipitate will form because we're going to adjust, okay, these values in a way to get equilibrium. We're always working toward it, okay? So I said thus a precipitate will form as the reaction will spontaneously move toward the reactant or reactants, in this case reactant because it's just magnesium hydroxide, as it approaches equilibrium, as it moves or approaches equilibrium. Okay, so Q versus K question. To get this, definitely you had to say whether a precipitate should form. That would be yes. Okay, and then you justify it. You had to justify it quantitatively by comparing the value of Q versus K. By the way, if Q was less than K, which means it had, again, don't forget, K and Q have the same formula. It's the products concentration, okay, over the reactants. And if the Q is smaller, let's just pretend it was smaller, that means you would have had more reactants and less products. And that means you'd be in this position, and then you'd be moving forward toward equilibrium, okay? And if that was the case, we would have dissolved more of the solid and not have any precipitate. Of course, that was not the case, but again, understanding that I'm trying to teach the concepts here. All right, so moving on to the next question. F kind of closes out this first question, and it states a separate experiment. The student adds nitric acid, HNO3. You should know that to be a strong acid, to decrease the pH of a saturated solution. That's a solution that has reached equilibrium, containing undissolved magnesium hydroxide. Does the amount of undissolved magnesium hydroxide increase, decrease, or remain the same as I add the acid? Well, you should recognize that magnesium hydroxide is a very weak base. It's an insoluble compound because it's a weak base. But nonetheless, a strong acid's going to react with it. So you would have to say decrease. Now I said the amount of undissolved magnesium will decrease. Okay, now you have to justify with these questions. And I stated that, hey, it's a strong acid. It'll completely dissociate. Thus, only a small amount of the acid will be needed to react with a small amount of moles of magnesium hydroxide. Now I'm showing off here. I took the molarity of the magnesium hydroxide and the amount of it, and this is the total moles of magnesium hydroxide. Now, of course, you got to times that by 2, and that'll give you the amount of hydroxide ions that's actually being reacted, but that's a small amount. Even if I times that by 2, you know, I'm going to get 1.2 times 10 negative 1.3 times 10 to the negative 4 moles of hydroxide ions, and therefore that's a tiny, tiny volume. I mean, a molarity. I'm not going to need much of that acid to reach that and neutralize whether it's a solid or the solution or the hydroxides in solution. So therefore, it's going to decrease. It's not going to take much to decrease all of it either. All right, so that's where I was headed there. And what's accepted here, I think all you needed to say that, hey, the strong acid would definitely react with this weak base, and therefore it has to. Now they're talking about the undissolved. Like, why would it go after the undissolved? Well, because the amount of saturated ions is so low. So it would, again, the acid would definitely take over and neutralize all the moles. You wouldn't need much of a concentration and a volume to, again, to react with, in this case, double the amount of 6.5. All right, so again, 1.3 times 10 negative 4 moles of hydroxide ions is just a very, very tiny number. It wouldn't take much. So clearly it's going to, you know, react and neutralize and make water with the hydroxides dissolved in the solution and or as a solid. All right, on to question number 2. So beginning another 10-point question, exactly where the points are, don't know, but here. I kind of like this beginning. I like the empirical formula and stoichiometry of the types of atoms, the ratios of the atoms in a formula. Like it a lot. So in any case, they're combusting a sample of ascorbic acid of an unknown formula to determine the chemical composition. Only the products of the reaction 0.240 moles of CO2 and 2.883 grams of CO2. And you should recognize that combustion, you're burning something. There are only two products, CO2 and water. You should recognize that. And we're taking also the idea that we're going to combust it with oxygen. Any case, they wanted to know the number of moles of H2 that was produced. That's pretty simple to me. Pretty straightforward stoichiometry, right? All I'm going to do here is very simply take the grams of H2O using the molecular mass of water and make moles, and then I'm going to say, hey, in a water molecule, okay, there are 2 H's per 1 O, and that's how I get my total moles. And I should recognize something from things that you've learned, hopefully, in your other class. In combustion analysis, okay, all the carbon, okay, from the hydrocarbon that was burned is locked up in the CO2, and all the hydrogen in this hydrocarbon, I know it's not quite a hydrocarbon, is locked up in the hydrogen, okay? And of course the oxygen is hard to deal with because you're of course dealing with the oxygen you're reacting with, but in this case they kind of simplified that. All right, so any case, what we're going to do here is we're going to take the moles of H, which we have here, and we know we should think about this. If we're going to build the empirical formula, what we're going to do is take these moles and do a mole ratio, and we're going to divide by the smallest number to get whole number ratios, and that's how we build the formula. So what are we going to do here? Okay, well, they gave me 0.2400 moles of CO2, and what do I know is that all of the carbon in CO2 came from the original carbon of the fuel. So that's easy one. Since there's 1 carbon per 1 CO2, the moles of CO2 is the moles of carbon. And they were very cute in this question in that they said that the mole of carbon to oxygen is 1:1. So they kind of eliminate the problem of the oxygen because we're reacting it with oxygen. So once I know the moles of carbon, boy, I know the moles of the oxygen because they said it was 1:1. I'm ready to get going here. All I'm going to do is I notice that 0.240 is the smallest mole, and I'm going to divide that smallest number through all of my moles here, and I get a 1.33 to 1 to 3 ratio. I can't put 1.33 into a formula, so what I do very simply is I find a number I can multiply it by to get a whole number, and I do that to all of them, and I did that. I times it by 3. So a little extra sauce there they had there to figure that out, and I got these whole number ratios, right? I can't put 1.33 atoms here, so I had to figure out a number to multiply all of these so I get whole number values. And again, it was 4:3 to 3 ratio, and just plug them in. Now I did write them 2 different ways because we're going to later use this as an acid, but it doesn't matter which way you write it. Okay, those are just 2 different one's a structural formula, one's a molecular formula, doesn't matter. Okay, any case, actually they're both molecular formulas with an H in front if you want to get technical. All right, any case, on to B, love and life here with a nice titration curve, because I love doing titrations. Okay, they're telling you it's a weak acid. Okay, well, you don't have to know, you should know that already because you should know your top 7 acids, and ascorbic acid is not one of them, but in any case, they were nice and told you that. And they gave us a titration curve, very, very nice. And let's talk about what they want. They want to calculate, all right? They want to calculate, let me zoom, okay, yeah. So they want to calculate the molar concentration of the ascorbic acid. How do I, rephrase that? They want to find the molarity of the acid I'm titrating. As you notice, the curve is going up. We're adding a base. We're driving the weak acid forward stoichiometrically until it runs out to the equivalence point. And we want to find its molarity. So again, I know people want to jump to MB equals MV. I don't use that. I don't like that. I like to go after the idea that the moles of the hydroxide equal the moles of the weak acid. I'm using HA as my weak acid for the ascorbic acid. And the first thing I do is find my equivalence point, which is the middle of this asymptote. And the most important thing I'm going to find is I'm going to find the volume at that equivalence point. And I found it to be 16 milliliters. And since I already know the hydroxide concentration, which is 0.055, right? Since I already know this, I'm going to convert that volume in milliliters into liters. And for the millionth time, you should know liters times molarity gives you moles, and moles of hydroxide. And I want my students to know that the moles of hydroxide at the equivalence point equals the moles of H+. When you do MV equals MV, you're just blinded by what you're really doing. Okay, that's my opinion. Okay, any case, so I get the moles of the H+. Very simple. And then since I'm building a molarity problem, you may say, Mr. Grotsky, we're doing the same math. I'm following. You're right, we are doing the same. MV equals MV is the same math. You're absolutely right. But again, I'm trying to make you understand the problems. And I do believe after 30 plus years of doing this, getting your moles and thinking of stoichiometry and acid-base questions as opposed to just plugging in a formula is better. So any case, you need to know the moles of the hydroxide equal the moles of the H plus at equivalence. Since we got those moles by what? Again, timesing liter times molarity of the base, and we know now we know the moles of hydroxide that are exactly needed to neutralize the acid, the H plus. Since I'm after the molarity of the H plus, it's moles over what? Liter. And so I know the moles of the H plus. It's equal to the hydroxide that was needed. Okay, the question is, what do I do for a volume? Well, I told you in the problem, or they told you, it wasn't my problem, it's not about me, that 10 milliliters was titrated. I'm going to convert that to liters because molarity is mole over liter. And there is my concentration. I know you could have done MB equals MB, and if you have to, go for it, I guess. All right, any case, that to me is a classic problem using the graphs, and hopefully you guys did this in your labs. I know that we did this many times over. Okay, all right, so any case, moving to II, from the titration curve, determine the approximate pK of the acid. For the millionth and one time, folks, the pH equals the pK at half equivalence. You should know that, okay? So if we know the equivalence volume is 16 milliliters, gave me, which represented the volume of the base that delivered the amount of moles that exactly neutralized the acid, well, half of that volume will half neutralize the acid. Why is that important? Because one half of the acid will become the conjugate base and another half remains. And when you have equal amounts of conjugate base and conjugate acid, the Henderson-Hasse block here, that really what I call the buffer solution, becomes zero. The log of the same number, whatever this is, over the same number as the log of 1 becomes 0. And hello, pH equals pK. So graphically speaking, we need to go to the half equivalence point on the graph, which is the 8 milliliters, half of 16. And as I showed you here, we're going to just find that approximate pH, which is equal to the pKa, because we've gotten rid of the log part, because that goes to 0 when you have equal amounts. So I get a pH of 4.1, which is equal to the pKa. All right, so that's what that's all about. Okay, so in any case, let's get on this, back on this horse. And so the pK is 4.1. It couldn't be any easier. These first two questions, if you're not getting them because you haven't used the graphs in your class, okay, need more practice, okay? But in any case, moving forward, those are straightforward. 3, or II, is the least straightforward, but not difficult math here. And it's just a question that doesn't appear too often, but actually has appeared. Last year, 2024, this kind of question was there, I believe. They want the value of the ratio, and people say, what the heck is that? Okay, well, that's the A negative, my friend, and this is the weak acid. What's that ratio? Well, my friends, that's part of the Henderson-Hasse block. So they want you to solve for this ratio. What do we know? We're going to solve for it at 4.7. So that's 4.7 goes there. The pKa we just solved for. Now we're just going to solve for this ratio. You say, well, how does that a ratio? Well, if you solve for this and get 10, it's 10 over 1, right? So if you solve for this and you get 0.1, that means you have 1 to 10 ratio, right? This one's bigger by 10. So in any case, you just plug them in and put the pK in, and we're just going to make the x equal to this ratio. Okay, very simple. So the log of x is equal to 4.7 minus 4.1. Okay, I'm just subtracting 4.1 to both sides. That's what I'm doing here. And I get the log of x is equal to 0.6. What do I do with that? Oh, very simple. What I do with that is I'm going to do, to get rid of the log of x, I do 10 to the x of both sides. That gets me the x, and it makes 10 to the 6th, and I solve for that. I get about 4. It's a 4 to 1 ratio. 4 is 4 over 1. Don't forget what we're solving for. We're getting about 4 to 1. So it's about 4 to 1 ratio. You have 4 times the amount of conjugate base. And it should make sense to you. If you're at 4. What was the number? 4.7. Think about this. 4.7, we would be around here. Well, if we're around here, we have a lot, we're way past the halfway point. Why? Because we added a lot more base. Okay, so therefore we're going to have a lot more base than a conjugate acid. The conjugate acid is going to be eaten up there. That should make sense. Okay, any case. Okay, moving on. All right, to the next question. So question 2C is a rate law formula. They give me a new reaction with our ascorbic acid. That's kind of the theme of question 2 here. And they're reacting with a triiodide, and in the problem they give us some experimental data that should really catch your eye in terms of a rate law, because they give you the trials, they give you the amount of the initial concentrations and the initial rate of the formation of the product. But more importantly, getting to the question CI, they're giving you the rate law and they're telling you it's first order with respect to the ascorbic acid. Okay, they're a funny way of writing it there. And so what they want you to do is just support the conclusion. This kind of FRQ seems to be a lot of giving you the outcomes, and now you explain that. I'm seeing that multiple times here. But so they want you to support the conclusion that it's first order, and this is really important, with respect to the ascorbic acid. When I first did this, I quickly did it the other way because they provide the evidence for the ascorbic acid staying constant and the triiodide having, okay, so that's a really good little distractor, or an evil distractor there for this question. So you have to be careful and make sure you read. So you have to compare trial 1 and trial 3. That's the one that makes the most sense because, again, as you can see from my writing, we're going to keep the triiodide constant. All right, and that's really important. Keep that as a control to know what happens when the ascorbic acid doubles and what happens to your rate here. It also doubles. Okay, and you should recognize that by the numbers here. And so how do you need to explain this? Well, very importantly, talk about your trials. So trial 1 are compared, as I said. We're keeping the triiodide constant, and of course you need to say that. Missing that, you miss this point. You have to keep that constant, okay, while the ascorbic acid doubles and the rate of formation also doubles. That's it, okay, showing that the rate is doing exactly what the initial concentration changes are for the chemical that we're actually looking for with respect to the ascorbic acid. So you had to make sure that you kept the triiodide constant, of course, and look at what happens to the ascorbic acid there. And I can see very easily, based upon the data they presented, that people could have done the opposite. You would not get the point if you talked about what the triiodide was doing, because they said with respect, okay, to the ascorbic acid. So it's first order for the ascorbic acid based on those changes in the experiment we just talked about. So moving on to II, they want you to calculate now the rate constant. And this is a very classic question, and it couldn't be any more classic here now that you have, and of course they gave you the rate law, okay, they gave you the orders because they said it was first order. Okay, and they gave us the rate law here, right? So, so we know it's first order for both. And if you weren't sure that it was first order for both, if you thought they were being sneaky, and they might have been, what you could have done is you could have looked here to make sure, and that's really a good thing to do. Don't take anyone's word for it in these types of little problems here. So if we want to make sure that it's first order with the triiodide now, we're going to keep the ascorbic acid constant, and 1 and 2, and we're going to see that, let's say we go from 2 to 1, the ascorbic acid stays constant, and the triiodide doubles, and you could see that the rate doubles. So if you weren't sure if it was first order for the triiodide, you could have went and gone and made sure of that. All right, they did give us the rate law, but again, I could just make sure things are consistent in their questions. Any case, once we know that that it's first order, we're going to use any trial. That's important you understand. We can use any trial because the rate law constant, just that, is constant, and it won't change no matter what trial you use here. So all I did was take the values given for me for the rate of the first trial, the initial concentration for the ascorbic acid for the first trial, and the initial concentration for the triiodide. So I just plugged them into my rate law formula, and then all I did was rearrange, and I solved for it. Okay, and using my calculator, I came up with 4.55 times 10 negative 4, and usually, okay, I would say almost always they ask for the units when it comes to a rate law constant. So if you didn't put the units, you lost a point. So this is definitely a 2-point question in my opinion. Okay, but or it's a 1-point question, not getting the whole thing right, even if you get the number right, if you don't have the units correct. So how do we get those units? Well, if you see that we have molarity over seconds here, and we just put this over here for a second. So the rate is molarity over seconds. Be careful because you know, this could be what? It could be hours, it could be minutes. In this case, if you check out the table, it is seconds, and that's going to be divided by, well, if you think about it, molarity times molarity is molarity what? Squared. Okay, and so when you cancel that out, you're going to get rid of this molarity and give 1 over here, so you're left with 1 over seconds over molarity, and that essentially is going to give you 1 over seconds molarity, which you can write to the S-1 or M to the -1, which just means 1 over for each of them. And that's not always going to be the same units there. Be careful. It depends upon the rate law. You could have a square here. Okay, in this case we didn't, and that would be molarity cubed on the bottom. That would change, your simplification. Okay, so that's important to make sure you understand that. So moving on, let's take a look at 2D. The triiodine ion I3 is significantly more soluble in water than elemental iodide. Well, for sure. I mean, triiodide has a charge that water can actually attract, and of course I2 is non-polar. It's not going to be very soluble because it doesn't have a negative or positive part, whether it's permanent like an ion or partial like a polar molecule, for water to really attract well and pull away from its own H bonding. Identify an intermolecular force, this is really the question, between the I3 and the water that's not present in I2 and water. Well, for sure, okay, I'll continue, which could explain the difference in solubility. Okay, very simply, okay, the I2 is an ion, okay, and it's got a charge, and it's going to track the partial positive of the H's. Looks like I have iodines here. Then I look at it, but it's water drawn on its side. Now that I look at it, okay. But and certainly this is called an ion dipole attraction. Molecule ion, I think, would be accepted as well. So this is basically, you probably drew these many times in your classes where you have, let's say, a sodium ion, and you would orient to the negative part of the polar water molecule in this arrangement, and the attractive forces, not a bond, between these negative end, the partial negative end of the oxygen, and the positive ion is this ion dipole. The ion and the dipole, fancy word for polar molecule. So that's straightforward. And that, again, if you missed this one, don't worry about it, but on to the next question. So number 3 here, the last 10-point question here, starts us off with a phosphorus molecule. And they tell us that it's a P4 molecule with a tetrahedral structure as shown in the diagram. And what they really want to do is, it's incomplete if you look at the Lewis dot structure, because all Lewis dot structures must show lone pairs. Okay, and so with 3A in the box, make sure it's in the box, complete the Lewis diagram for P4 by drawing non-bonding electrons. So we needed a lone pair for each phosphorus. Where you put them was not important. The idea, though, is very important, that there was 5 valence electrons. If we get up close and personal here, we understand with those 5 valence electrons, okay, that we need to share 3 more and make 3 bonds to complete the octet. So it makes sense that each of these phosphorus would have an electron here, and then the other phosphorus would donate the other electron to make the bond, and we would have our octet, leaving us with a lone pair. And you just think about nitrogen, who's in its same group, makes them classically have lone pairs when they fill their octets, for instance ammonia, okay, for the same reasoning. So in any case, you need a lone pair there to fill that octet. And let's continue on. In 3B, they give us a reaction with the white phosphorus, a tetrahedral molecule reacting with oxygen. And very important, they tell me something. They tell me that it's thermodynamically favorable at that temperature, okay, which we're going to need for II. But here they're just saying in BI that the entropy change of the reaction is negative. Okay, that's also a very important piece here. So they're telling you here it's negative. Another part of this FRQ where they're coming out and giving you the conclusion, and they want you to basically talk about why. Okay, kind of interesting FRQ this year. But in any case, why is it negative? I would think you would have to, I would like to actually come up with that yourself and justify, but they're telling you it's negative, and then they want you, very important, to say using particle leveling reasoning. And the reason that's important, because some people, like myself, love to teach what entropy is all about. As people go over this and think about entropy as just disorder, they're really missing out what entropy is. Entropy is the second law of thermodynamics, or it's part of the second law of thermodynamics, which states that the universe's entropy is always increasing. So what does that mean? What it really means is that the dispersion of energy, concentrated sources of energy, are spreading out. And one part of energy is the dispersion of particles outward. There's molecular motion that can spread out as well. And so when I think about particle level reasoning, or when I think about the entropy of a system, okay, we're always talking about how are these molecules spreading out their energy, or are they becoming more concentrated? And you can recognize very clearly that P4 plus 5O2 making P410, we're putting things together. If you want to think of becoming more ordered, that's fine, but you're really concentrating all those molecules into bonds, and that is going against the second law of thermodynamics. But more specifically, if we're talking about delta S of the system, that's what we look about, that's what we actually measure in chemistry, delta S of the system. They don't talk about the surroundings too much, but the point is that is tied to how well the particles will disperse their motion energy, their kinetic energy. And in this case, we have 6 moles of free molecules becoming 1 mole, okay, of one solid. So the degrees of freedom, and that's the words I love to use, is going to, in this case, decrease. Particle level reasoning. So the number of free moving individual particles are decreasing as we go from 6 moles of reactants to 1 mole of products, and therefore the entropy of the system is going to decrease. Well, because we are not spreading out, we're making a concentrated source there. Okay, so the way that I express this is that the delta S of the reaction is negative due to the degrees of freedom, due to the 6 moles of reactants that reacted to produce 1 mole. But I can certainly add here the idea that, and I think it's important to add this, that there also is 5 gas molecules becoming part of one solid. Or you can say 5 gas molecules becoming part of a crystal. I think that would be a better way to say it. Part of a crystal lattice. So there are really two answers here. The 6 moles becoming 1, or if you can recognize clearly that there's going to be 5 gas molecules becoming part of a single crystal, and therefore the degrees of freedom are also decreasing. So there's two ways to answer that. I think they would definitely take the 6 to 1 or the 5 gas. Either one would work there. I chose to focus on the 6 to 1, but you certainly could have definitely talked about the idea that 5 free moving gas molecules that can fly around the room are now trapped in a crystal where they can only wiggle in their fixed positions. Okay, so certainly, in my opinion, there were two clear ways to support the fact that the entropy of the system was decreasing. But the words that I think that are very important are degrees of freedom. I think that's a good way to talk about that. Certainly isn't the only way. All right, so on to II of 2b, and I said before when I started this question, I said that it's important to recognize that saying something is thermodynamically favorable at 298. Okay, so this was an important piece of information to say that at that temperature, delta G is negative. Okay, that's important. All right, so in any case, we get to II, the enthalpy change of a reaction is also negative. Okay, another piece of information. A student claims that the favorability of the reaction is driven by the enthalpy and not the entropy. And that is 100% true. All right. If the students claim correct, of course I'm saying true here, and then justify. Make sure you somewhere say, is it supported? I know when I'm grading practice, I see students support the claim, but they never tell me if it's correct or not. So come out and say it. So make your first statement. So I said the student's claim is correct. Okay. And then I'm going to justify with my work here. Now, stuff right here is I'm using to teach with. When I think about delta H, delta S, and delta G, I come up with this hugely important thermodynamic equation that you have, and sometimes you calculate with. But this is the one I think about because delta G measures whether a reaction is going to be thermodynamically favorable. That negative tells me that free energy is released, but more importantly, it tells me that the entropy of the universe is increasing. And there's two parts. There's the entropy of the system, are the degrees of freedom of the molecules increasing. In this case, they were decreasing, and that's why I would write a negative here. Okay, originally there's a T and there's a minus, and they told us it was exothermic, so the delta H is negative. As again, there's two parts to whether a reaction is thermodynamically favorable. There's two conditions that we have to consider, and that is going to be the entropy of the system. Are the molecules spreading out, or are they getting more concentrated? Well, in our example that we talked about in I, they were getting more concentrated. So that is an unfavorable condition because that leads to part of the universe's entropy, what? Decreasing. And then we have to consider the surroundings. The surroundings entropy, okay, is increasing as we release heat. Being exothermic means it releasing heat. And again, if I'm losing you because your teacher doesn't talk about this, to totally understand this, think about a system as this little box. And inside the box, so this is the entire universe. And if we're going to release heat, that means the surrounding, that's the air, let's say, or the molecules around here, are going to move faster, and they're going to spread out more. And we would say that the entropy of the entire universe is increasing due to the surroundings. But inside the box, we measure the entropy of the system by what the molecules are doing. So we already know it's unfavorable here because we're concentrating the molecules in the box. But if we're releasing heat outside the box, we're making the molecules go faster and they're spreading out more. So that's a good thing. So we have a favorable condition being exothermic, but an unfavorable condition. So how do we make a negative delta G, which we know makes it spontaneous, which is the same thing as making the universe clearly increase in entropy. Well, we have to do is we have to limit this unfavorable condition. See the T in front? That's why we need a lower temperature. Okay, and by the way, if you do your math plus plus, you can see a negative plus a positive. The only way for this negative to result is this exothermic favorable condition has to win out. One way to do that is to lower the temperature to minimize the unfavorable condition of the degrees of freedom decreasing that we saw in II. So if you caught any of that, great. If not, here's my answer. The student's claim is correct. A negative delta H and delta S will result in a favorable thermodynamic reaction, negative delta G, when delta S is negative. I'm really important I'm trying to talk about all three of these as they relate to each other. Okay, and delta S is negative. So somewhere, somehow, I'm mentioning all those values. And when that's true, okay, so if the temperature is decreased, which allows, let me just read this through again. The student's claim is correct. That's the point I want you to make. A negative delta H and a delta S, so both of them negative, will result in a favorable thermodynamic reaction, negative delta G, when delta H is negative and delta S is negative if, that only is true if the temperature is lowered to minimize that we just talked about, which allows the delta H's negative value to be greater than that. So what you needed to talk about, in my opinion, to justify the fact that we have one favorable condition and one unfavorable, we have to make sure that we minimize this part of the equation, and that's what I'm talking about here, and you've seen this before. So I really believe that you needed to talk about the delta H's exothermic value had to be overwhelmingly more negative than the positive value of the later half of that equation. So that's why I have this big positive here. And how does that happen? We have to have a smaller temperature to do that. And by the way, you could also have mentioned the fact that it is enthalpy driven because we have that delta H of negative that drives this reaction because it's favorable. The only way that this could be a negative delta G is the exothermic condition that again overtakes the unfavorable condition. And again, I'm just kind of rehashing it and saying it a different way, but it's definitely enthalpy driven. And those enthalpy driven reactions are best happening when temperature is lowered. So again, so on to 3C, we've got ourselves a reaction here with P410 reacting with water, making a aqueous solution. We have a calorimeter. We're going to do some calorimetry, of course. Nice little picture that doesn't really help us, but in any case, we've got ourselves some data here. And the question goes, calculate the amount of heat Q released during the experiment in kilojoules. Whoa, watch out for that. All right, in kilojoules. Got to make sure that we answer in kilojoules. Easy to miss that. Also, they said assume the specific heat of the solution is the same as that of the water. Oh, that's a really important hint because now we're dealing with the Q of a solution, which means we're going to use our thermal equation, Q equals mc change in T, but we are going to understand that's going to be the mass of the solution that's occurring in the calorimeter. Okay, remember we're dropping P4 O10 into water. It's going to create a solution, and of course it's going to react, and we're measuring that energy change. So the biggest mistake I can see people missing here is that they'll forget to add these two, since they kind of gave you that hint that there is a solution. So basically we're going to measure the Q of the solution. And they also said that the specific heat is about the same of that of water, so we can use that value that's given to us. And also when we do Q equals mc change in T, don't forget temperature final minus temperature initial, so that we get the right value of the sign, positive or negative. I know they're saying how much heat is being released, so you may just throw a negative in there, and I get why you would do that. But really, if I'm going to be teaching this the right way, we should just let the math dictate the signs here. So temperature final, since the temperature went up in this system, that means that the energy from the reaction went to the water. we should know that the Q of the solution, that's what this is going to be positive, right? So when we multiply these values through, we're going to get a positive amount of joules. Of course, I'm going to convert to kilojoules because that's what they're asking for. If you did not, you would definitely lose at least 1 point here. If this is a 2-point question, I'm not sure if it is or is not. Okay, and there's my answer to the appropriate level of sig figs. Although they're not looking at sig figs that carefully here, it's a good idea to round with the correct number anyway. And I'm looking at the fact that they're giving me 4 and that my temperatures have 4, so I'm rounding to 4. Any case, that's the first part, but I'm getting a positive value. And again, you could have thrown a negative in there, but it's important to understand we just solved for the Q of the solution. And for those that are getting lost by my explanations here in terms of the size of the charge, I think you need to look at and draw yourself a diagram, and I'm going to do that quickly so you understand. So the calorimeter is supposedly a closed system. It is not. Energy does leak out, as that's a classic question as you probably have seen in your practices. But I like to think of the reaction area in a calorimeter. In this case, the reaction is occurring all in the solution, so this is just a nice way to think about it. It's not exactly how it's happening, but what's happening definitely is that because the temperature is increasing, we know that energy is flowing out of the reaction into the solution. Remember, the vantage point that we're doing is in calorimetry is we usually measure, we do measure the surroundings, right? We're measuring the surroundings. In the case of the reaction, we're measuring the solution. So in calorimetry, we measure the surroundings. A lot of times that's the water, okay? And we reflect what's happening to the reaction by what happens to the surroundings. We can't measure directly what's happening to the reaction because, hey, its mass is changing. Because if it's a chemical reaction, of course, like this is, its specific heat will be changing over time. So it's an impossibility to measure the reaction directly. But because of the first law of thermodynamics, which states that energy is conserved, all the energy that releases from the reaction, okay, has to go into the solution. So if we measure what's happening in the solution, we can reflect that back to the reaction, which is basically what the next question is. So in any case, I'm getting a positive value for the heat because the surroundings are taking in energy. That makes sense. The Q is positive, and I like the math to drive that. All right, to the next part. So in any case, I and II go together here. Very important question, or very important group of questions here. So I've got my positive energy that the water absorbed. But if you look at now CII, they're asking for now the delta H of reaction, which is a state function. It basically takes the Q, okay, that the reaction was undergoing, its change of energy, and dividing it by how much mole to make that a state function, not a pathway. Oh, more to talk about another class, but we're going to convert that to a delta H by dividing by moles of how much actually reacted. But more importantly, okay, I want you to understand that now we're after the Q of the reaction. We measured what happened to the surroundings, okay? So it's really important that we reflect the reaction by saying Q of the reaction equals negative Q of the calorimeter. You could say negative Q of the solution. It doesn't really matter. It's the surroundings that we're using. And I'm doing that to say that, hey, whatever happened to the surroundings must be opposite in charge to the reaction. So if the surroundings is absorbing heat and going up, then the reaction's releasing the heat. Okay, so that's where my negative results. So I'm going to take the value here that I got, okay, from the calorimetry and measuring the surroundings, and now I'm going to make it negative. Okay, negative of what's happening here to change the sign because, well, it's the opposite end of the energy flow. Water, in this case, the solution absorbed, the energy must release. So it makes sense that the Q of the reaction must be negative. It's losing heat for the water to gain heat. And now I have a negative Q for the reaction. I know they came out and said that here, but that's really confusing to me. Okay, I think you should always break it down this way and let, again, the math dictate what's happening and make it make sense to you in your head that the Q of the reaction now, with respect to the reaction now, it's got to be negative. It's losing heat. How do I know? The surroundings went up, and you should know that a delta H that's exothermic is going to be negative, and the temperature of the surroundings always increases. All that should fit nicely. Any case, to solve for my delta H, I'm going to take this Q and put it in here, and it's negative now. now we're looking at the reactions point of view, and then we're going to take the 0.1 grams of the chemical that we're after. Even though it did react with the water, it's about this chemical, and we have the grams. They gave me the molecular mass, and of course now we're going to convert to moles. This probably could be a point on its own, and then the right answer with the right sign. Any case, I'm going to put these moles, of course, on the bottom, because Q of the reaction is mole of reaction. And again, they're giving me the units they want, so kilojoules over moles. And do the math, and you get negative 451. Make sure you write your units, really important. Okay, and it should make sense that my delta H is negative, okay, as the environment temperature goes up there. All right, so on to the next question. So in 3D, the chemist weighed out 0.110 grams again and 100 grams of water to perform a second trial. But in this second trial, some of the solid P4O10 stuck on the weighing paper and was not transferred. That means you have less of it. Given that P4O10 is the limiting reagent, that's important here. That's important. That means that the total amount of products, or in this case heat, is dependent upon how much of the P4O10 I have. And because we have less of it, because it's stuck to the weighing paper, we're going to have less heat released by this exothermic reaction that we found from 3C. Here comes the question. Would the change in temperature for the second trial be greater than, less than, or equal to the value? Answer that question first. Make sure you do so. It's less than. Don't just justify your answer. Less than. Come out and say it. All right. So the change in temperature is going to be less because there's going to be less heat that is released because there's the less of the chemical that we just solved in 2C that we found was exothermic. We found that delta H, okay, was a negative value, which means energy is released, and essentially the water temperature went up, or the solution's temperature went up in temperature, depending upon, of course, how much energy is released. Well, if that energy is released because of this chemical's delta H, if there's less of it, there's going to be less heat released. Okay, so I said in the second trial there'd be less due to the smaller amount of moles of the limiting reagent reacting. If there was a smaller amount of P4O10 that reacted than the original, then less heat would be released and the final temperature would be lower, decreasing the change in temperature. Look what I did there. I said because you had less of it, and because the P4O10 is responsible for the heat release, okay, less heat would be released and the final temperature would be lower. Look what I did there. There's going to be the final temperature. Remember, the final temperature went up from some room temperature or some lower value. That final temperature is not going to be as high. So the change from the original would be lower. Okay, so make sure you spell that out and don't get too vague here. Not a very difficult problem, I don't think. And they gave you a tremendous, I think, hint here by saying, hey, that's the limiting reagent. That's the one that, dictates how far the reaction goes. In this case, how much heat is released. Think of heat as as a stoichiometric quantity for sure. All right, so moving on to 3E. Okay, which is a nice little Hess law problem. They gave you the equations, they gave you the overall reaction, and they wanted to know the delta H of the formation. Don't get lost in the sauce with the heat of formation. That's just a type of reaction. They just wanted the resultant delta H. And what you should know that is that if you have the enthalpies of individual reactions that can be manipulated to get the overall, the manipulation you do to each reaction needs to be done to the delta H, okay, because that's again a stoichiometric relationship of how much heat based upon how much of the reaction you have. Notice it says mole of reaction, so if you change the stoichiometric coefficients, you're going to change how much of the mole of reaction you have. So in any case, we needed to basically take these two reactions and we needed to manipulate them to get the overall. So the biggest thing I saw was, do I have to flip any of these? And I noticed I saw P4 solid was here, and I saw PCl5 was here. So I knew that both reactions had the reactants and products in the same place, so there was no flipping. And if I had to flip, I'd have to change the sign. But I did know right away that I see 1/4 P4 And if you look, I only have, there's one. So what I had to do here was multiply the entire and distribute 1/4 to each of these. And that would give me my 1/4 of my P4. That would, you know, you take your 1/4 times your 6/1, you get 6/4. And that would be 4/4. That would go to 1. And you can see in your answer here, the overall reaction of PCl5 is 1. Okay. And you may say, what am I doing with this 6/4? Well, if you look here, the 6/4 is really 1.5. And looks like I'm adding to 1 here. And why am I doing that? Well, if I look up here, if this is 1.5, right here, I've got to add it to the chlorine down here to give me overall. So 1 plus 1.5 gives me 2.5, and that's the same thing as 2.5. And also recognize the fact that we're going to cancel. This is now 1, so this can cancel. Okay, and I'm left with PCl5 and 1/4 P4. So everything works out. All we had to do was multiply by 1/4. We can't forget that by multiplying by this 1/4 by this equation to make everything cancel to give an overall, I've got to times this by 0.25 or 1/4. Okay, so what you do to individual steps to cancel the overall, you've got to do to your delta H's. Okay, and so all that was timesing that by 1/4, and of course that's what I have here, and then add these together. All right, and you get your overall. Not a very typical, I should say typical, you're not seeing these too often, but definitely a very typical chemistry question, okay, where we are using the individual reactions, okay, to get the overall here. Okay, so I hope that makes some sense. All I had to do to balance those two equations was times by 1/4. You had a little bit of understanding of 6/4 becomes 1.5. You had to add, okay, these chlorines together to get the total number of chlorines. Okay, we did cancel our PCl5, and we did need the 1/4. So a lot of nice hints here. I had to multiply by 1/4, and the math does work out. The 5/2 is strange, but think of it as 2.5. Cl2s. You might be asking, why do they do that? Because you don't want to write 2.5, 5/2, and in essence, you really can't have 2.5 chlorines, but they will do that to express the lowest whole number ratio of a product when you write a heat of formation. Remember, heat of formation reactions, we want to make 1 mole of the compound and measure that energy, which goes into tablature that you probably have used in other, you know, a delta H of a reaction equals the heats of formation. Remember, the heats of formation, the sum of the heats of formations of the products minus the reactants. But in any case, if you were to ever have to write a heat of formation reaction, you're going to need to make it equal into 1 mole of these products here, and then of course you're going to have fractions inevitably for a lot of reactions. Okay, so in any case, I know the fractions are weird, but essentially what you're doing is timesing by 1/4, okay, and then adding their delta H's together. There's always an easy solution to every one of these problems, okay, even though they may look weird. On to the next question. So in question F, we have a particulate diagram of the 3 gases we saw in the previous question. And what we're going to do here is we're going to calculate the Kp for the equilibrium mixture. And a very important hint here is they said that each particle in the diagram represents a partial pressure of 1 atmosphere. Okay? And so all I had to do was count the individual gases and times them by 1 atmosphere. All right, and that gave me the equilibrium values that I needed to plug into the equilibrium expression, right? I needed an expression first. All right, so that is important to understand, that I had to do products over reactants, coefficients become exponents, and solids and liquids do not apply. You may get a point here. I'm not sure. I haven't looked through the points for the expression, but you definitely need the expression. I wrote it. I throw the P in here. Some people say you don't need it, but again, it's just products over reactants. Coefficients become exponents. Solids and liquids do not apply. These are all gases. You should have parentheses if you are writing an expression for an equilibrium reaction that has partial pressures. Okay, any case, just by counting and timesing by 1, what did they say? Every single particle represents 1 atmosphere. So again, I had 6 for the chlorines. That gave me 6.0 atmospheres. I had 2 for the PCl3. That gives me 2, and there's 5. And I times that by 1, and I just plug them in. Okay, so pretty straightforward. If you didn't know how to write the expression or had it backwards, I can see how that would be wrong. But again, that gives you the 0.33. And by the way, you didn't even have to. You can just put the 6, 2, and 4 particles in there, because what do you know about a mixture is that the number of particles, the moles of each particle, is proportionate to the individual partial pressure of each gas. All right, so again, I think that's pretty straightforward. Let's finish this out. And here comes the question. I really like this one a lot. Does the Kp increase, decrease, or remain the same when the temperature is increased? Okay, so now we're adding a stress to the system that's in equilibrium. So this could be talked about in terms of Le Chatelier's principle. Okay, but I didn't come out and say that. You could have. But when I think about what happens with temperature increases equilibrium, I think that I got to know what's happening in terms of it being exothermic or endothermic, because now it's a stress related to a temperature change, and I have to know whether the reaction's exo or endo. So they gave me that this is an exothermic reaction. Okay, now what do I need that? Well, because if you're going to increase the temperature, we should know that an increase in temperature is going to favor the endothermic pathway. Okay, that's just something you need to know. A decrease in temperature, okay, is going to increase the exothermic pathway. So because this reaction is exothermic, and I'm just going to write, I'll look at this reaction here just to just simplify things. I'm going to make it, hey, look at A plus B makes C, and then I put the heat in here like it's exothermic, it's releasing heat. And if I think about Le Chatelier's principle, I'll make sure I have a double arrow here, because it is an equilibrium. There's a stress and there's a response. The stress is that we're going to increase the temperature. The response by the reaction is to lower the temperature to regain equilibrium. So what's going to happen here is this reaction is going to lower the temperature by using it up and moving spontaneously in the forward. Think of heat as like a reactant. We're going to use it up as we go in the reverse. So we always favor the endothermic pathway. And by them telling it was exothermic, we needed to know that now this reaction is going to shift to favor more reactants. And down here, if Kp or any equilibrium constant is really products of reactants, coefficients become exponents, and solids, liquids imply. If we're going to now shift to the reactant side, we're going to make more reactants than we have at equilibrium, and we're going to lower the products than we have at equilibrium. And now the equilibrium is now going to find a new position that favors more reactants and less products. And both of these arrows, if you lower your denominator, increase your denominator and lower your numerator, it's going to lead to a lower value. A lower value of your equilibrium constant is going to be a position that favors more reactants. So what's going to happen is, as I said, the value of the Kp decreases. It's got to get smaller, okay, because it's going to favor more reactants. And the reason why is because this reaction is going to shift or move in a direction that favors the endothermic pathway. it was established that they gave us a negative value. So any case, that's what I said here. So it favors the endothermic pathway, which is the reverse reaction. If the reaction favors the reverse reaction, the amount of reactants increases and the amount of products decreases to a new equilibrium position. Yes, this is Le Chatelier's principle, okay, for sure, but you really need to spell out, in my opinion, that the reaction is going to find a new position that favors more reactants, because it is exothermic in the forward, which means we have to go in the reverse to favor the endothermic pathway, because a temperature change, that increase in temperature always favors the endothermic pathway, which is in the reverse in this case. A decrease in temperature favors the exothermic pathway. It's something you need to know. All right, on to the next question. So number 4, the first of the last four-point questions. I found these questions in this test, in this FRQ this year, 2025, to be very, very reasonable, as is most of this FRQ, since the post-pandemic tests have been a little easier, but these particularly were the place to clean up and make some points here. So if you made some mistakes here, let's get to it. So for A, they want to identify the hybridization of the valence electrons in the carbon atom in the formaldehyde H2CO molecule. And very simply, if you got this wrong, you need to understand that there are 3 regions of electron density that are repelling themselves evenly, because essentially these electrons have the same density, they're the same type of orbital, and so if you're counting 3 regions, or they call these electron domains, we know that an S plus 2 P's have mixed together to make 3 equal orbitals, and we call that sp2. Notice the trigonal planar, a 120-degree bond angle. This is VSEPR theory. So the idea that these orbitals, these regions where electrons exist in these 3-dimensional standing waves of probability, I laugh because it's, it's a strange concept, repel themselves equally because each of these 3 orbitals, okay, have the same electron density, and they repel themselves in this trigonal planar shape. They weren't asking for the shape, but you notice 3 orbitals, so S and 2 P's, sp2, each one is an sp2 orbital. All right, you don't need to say that there are 3 electron domains. I'm just kind of teaching that through. All right, so in any case, it's sp2. On to for B. In the diagram provided, draw a single dashed line to represent a strong hydrogen bonding attraction between the methanol, the alcohol here, and the formaldehyde molecule in the mixture. So I chose that this partial positive region, okay, was attracted to this partial negative region, and H bonding is when you have an electron deficient H that's bonded to a fluorine, oxygen, or nitrogen. The 3 most electronegative atoms are pulling this pair so close to the oxygen that we're dangling essentially a proton, right? Hydrogen has 1 electron, 1 proton. Due to Coulomb's law, that's very, very positive. And it's going to attract the very electronegative end of another F or N. So this is an H bond here, okay? And what you should recognize is what is not electron deficient. You should not have any carbon H bonds. So any of these H's are not electron deficient because this pair of electrons are almost shared equally here. So we needed to show that region. And of course, if I look carefully, where else could I have that? If I'm not mistaken, that's really the only place that I can see where the molecules are placed to have that. If you were to draw a dot here, this would be wrong, because again, this is not electron deficient H. This hydrogen needs to be attached to an F or N to have that. So that would not be. So really the only place that I can see, okay, that is demonstrating the H bonding correctly or in a position to support the idea of H bonding is where I put this dashed line, okay? So any case, that is the only answer I can see based on positioning. They were really trying to set you up to show possibly here or here And of course, that wouldn't be H bonding for reasons we've just explained. Okay, so we're going to go back here to C. And see, we have some physical changes going on here. This is 4C, and they gave us melting, boiling points, and enthalpy of vaporization, all physical changes. We're separating these molecules based on their attractive forces, and we can see that the boiling points are markedly different here, meaning, of course, that they have a different amount of energy needed to separate them. Notice the enthalpy of vaporization follows suit here. Okay, what I mean by that is it takes more energy to separate this liquid, okay, into a gas, right? And so the ones that require more energy to boil require more energy to vaporize. The same kind of concept. So enthalpy of vaporization is actually the energy needed to separate from a liquid to a gas at its boiling point temperature, and this one, of course, is an indication of that as well. So in any case, CI, propose a temperature which the mixture should be cooled so that the alcohol and the formaldehyde will both be liquids. So I need them to both be under their boiling point. So if I look at the 2, I see 254 is certainly lower, okay, than the 238, so something under 254. I chose 250, but be careful, any number under 250 won't work because you want to be under the boiling point, but you want to be greater than the melting point, right? So because if we chose a number like 170, both of these liquids, okay, would be solids now because the melting point is 176. So you have to be lower than 254 but greater than 181, and that's what I put here. Okay, so that we would be a liquid. That's the key there. Okay, so remember, anything below a melting point means that you're freezing. Anything above the melting point, you're a liquid. So we had to be within that. So we have to be below both of the boiling points and above both of the melting points, and that's why I have that range there. So anything less than 254 but above 181 works, okay, for that point. And then CII is that they want you to use the enthalpy of vaporization. Basically, it's a kilojoule per mole, and it's because it's got a mole there, you can use stoichiometry. They want you to measure the energy it takes for a certain amount of grams of the alcohol, okay, to condense. Now you say, oh my gosh, what's condensing? Well, they're just kind of making you understand that the energy to vaporize is the same energy to condense. If you think of a heating and cooling curve, in this case it'd be a cooling curve. Okay, there's a gas, there's the phase change, there's the liquid, there's the next phase change, which would be the freezing phase change. And you should recognize this to be the gas, the liquid, and the solid, and energy is being released, and this is the phase change from gas to liquid. So, and of course it's the phase change from liquid to a solid, which is the freezing. But the point I want to make here is that whether we are going to vaporize or whether we're going to condense, okay, vaporization would be going this way, and of course condensation would be from gas to liquid. It's the same energy. So the enthalpy of vaporization is also the enthalpy of condensation, if that got you. So basically we call this phase melting or freezing, and you should know that the melting point is the same thing as the freezing point depending upon whether you're absorbing energy or releasing energy, and the boiling point is the same as the condensation point. So what they were trying to get at you is that you understand that the condensation is just the opposite of a gas to a liquid, but it's the same energy change. It's only going to be actually released as opposed to absorbed if you're trying to vaporize. Any case, so what we're going to do here, because it's an energy per mole right there, we need to be in kilojoules, and I'm sorry, we need to convert our grams to moles. Okay, the unit is already in kilojoules, so because it's kilojoules per mole, we're going to take our grams given, go to moles, and they're very nice. They gave you the molar mass, which again is telling you should be in moles, so it's kind of a big hint that you're going to convert to moles if they're giving you the molar mass. and we're going to use our units. We're going to get our moles here, and then we're going to use the delta H value, which is a ratio of kilojoules per mole, which is a converting factor, and convert to how many kilojoules it's actually going to be released for the gas to become a liquid. Now, you don't need a negative sign here or a positive sign. You just want how much energy will it take. Okay, and notice they said that the energy that will be removed to condense, right? Because it's an exothermic. We're going down in energy, at least we're releasing energy for a gas with higher energy become a liquid there. So in any case, if the condense caught you off guard, hopefully this makes more sense now. All right, as we go through a cooling curve idea. Okay, so on to the next problem. So number 5, based on VSEPR theory, predict the geometry, and I guess we have to assume the molecular geometry around the SI, unless they say electron domain geometry, but it's all going to be a molecular geometry around the silicon atom in compound Y. And I kind of try to make this simple by showing that there are going to be 4 electron domains that are going to have to be equal in their energy or their density and their size, and therefore there's 4 electron domains, so that means you're going to need an S and a P and 3 P's, and that's why it's sp3 hybridized, and you don't need to know that, but you should know that something that's sp3 hybridized that has 4 things bonded is a tetrahedral, or 4 things bonded to 4 equal orbitals, okay, is a tetrahedral. Very simple, straightforward there. Not much more I can do there for that. But I always tend to think about what's the hybridization first. Again, this is sp3. In the sp3 family, we have a tetrahedral if there are 4 things. If there's 1 lone pair, it's a trigonal pyramidal, and if there's 2 lone pairs, it's bent. That's the way that I kind of teach that. So it's kind of the same kind of question. So VSEPR theory is kind of playing its hand in a couple of questions already in this test, which I think they gave you very simple, straightforward questions. Tetrahedral, okay? And the other one was trigonal planar, but they were asking for the sp2 in that case. All right, on to 5b. A student claims that compound Y has a higher boiling point than do of compound X because compound Y has stronger London dispersion forces. Do you agree or disagree? Justify your answer. Okay, again, if they're going to ever ask you to agree or disagree, the first thing you need to do is hopefully have the right 50-50 shot here. Hopefully it's not a 50-50 shot, but you need to say you agree or disagree. Okay, if you just go into justification, you probably don't get the point here. So why does compound Y, okay, or the claim is, why do you think the student thinks compound Y, or does compound Y have a higher boiling point? It does. And the student is claiming that it's because of stronger LDF forces, London dispersion forces, which we should know is the type of attractive forces between the cloud of electrons that interact and distort a little bit to make a momentary partial negative and positive molecule that stick together. Every molecule has these clouds of electrons outside of their nuclei, some bigger, some smaller, in different shapes, and that affects the distortion and the strength of the London dispersion forces. So the idea that compound X has weaker LDFs or Y has stronger, we have to look at a couple of things. Number one, we have to look at the shape. Shape affects how the cloud can distort, and they have the same shape. You should also be aware that pi bonding, that double bond, okay, that exists, allows electrons to be delocalized, can also create more electrons being able to move and distort. This doesn't have any double bonds. So now we're just down to who's got more electrons. And we should recognize the fact that silicon is under carbon and therefore has got more electrons. It's an N equals 4 element, whereas carbon's an N equals 2. So clearly silicon's got more electrons. So there's going to be more electrons in that cloud that can shift, and we call that more polarizable. So I'm going to agree because, again, the shapes are the same. And more importantly, in this case, it has more electrons. So I said I agree the compound Y and X both have similar dipolar forces and H bonding. Now I thought it's important to mention that if the reason that one has a higher boiling point than another, and if we're just looking at LDFs, then we're going to have to assume the other forces they could have are similar. Now they both do have H bonding, as you should be able to identify right there. That's an electron deficient H bonding to an O or F or an N here. So they both have H bonding. They both are slightly polar. Okay, so what we would say, and I would say and clearly say, that the H bonding ability or opportunity is the same, and so is the strength of the dipolar forces. They look about the same asymmetry, so I would think dipolar forces and their H bonding are similar. Therefore, this does open the door for the LDF forces to be the difference here. So in my opinion, I do think you need to first talk about the fact that they have similar dipolar forces and H bonding, and therefore the difference in the LDF can tip the scale for the entire intermolecular force being stronger or weaker for another. So I do believe that you do need to talk about the other forces here. Okay, and that's what I did here. But they do have different LDFs. So the tipping of the scale for the boiling point, remember the boiling point is due to how strong the entire collective intermolecular forces, which is a cumulative effect that you should understand. So I talked about that they have similar dipolar forces in H bonding, but they do have different LDFs. Both compounds have the same shape with 0 pi bonds. Remember, pi bonds allow for electrons to move, but compound Y is more polarizable. It's a nice catchphrase. Okay, due to having a larger number of electrons, because silicon has more electrons than carbon. So hopefully you navigated and understand that difference there. But I do believe that first part, when you deal with intermolecular forces questions, it's really, really important to describe all the forces. In this case, I thought it was absolutely important to do so, to say that, hey, for the difference to be LDFs, the other two forces or the other forces have to be similar. Okay, on to number C, or letter C of question. What we got here? Question 5. Yeah, we're getting there. All right. So an equimolar mixture of the two compounds is heated when the mixture reaches 82, which, by the way, is the boiling point of the compound without the silicon. That's compound X. Let's put that in order. Yep. Okay. Which compound will have a higher vapor pressure? Well, clearly, the one that has a higher vapor pressure. Now, vapor pressure really is the force due to liquids evaporating from their liquid phase. So if there is more evaporation occurring at that interface of liquid to gas, you're going to have more pressure forces pushing upward on the liquid. You can always think about a rattling can on water, or a pot rattling if you're boiling and you put that on there. But the key here is that who's going to have a greater amount of liquids evaporating? Well, who has weaker intermolecular forces? Well, we just established in B that the entire intermolecular forces, or the LDFs, are weaker in X. And since the H bonding and the dipolar are similar, compound X has weaker intermolecular forces. And another way to understand that is that a lower boiling point always suggests that it takes less energy to separate that liquid into a gas phase, because the attractive forces, or the intermolecular forces, are weaker. So this is screaming weaker forces. That's why 5B was easy to navigate. Okay, so I said compound X will have a higher vapor pressure than compound Y because it's weaker intermolecular forces that's reflected in its lower boiling point. Now, I know that some people might say that, well, if we're at 82, isn't that the boiling point of compound X? And it is. And then some people might be able to say, well, okay, well, if it's reached its boiling point is when the vapor pressure equals the atmospheric pressure. And so we would say that compound X is matching the atmospheric pressure. Well, Y isn't. I'm not sure about that answer, because when you're in a mixture, okay, the vapor pressure is lowered for both, but you could say that compound X is closer to the atmospheric pressure. I'm not sure how they would deal with that, but we don't deal with vapor pressure lowering as a colligative property, so they probably would allow that if the one that has reached 82 is boiling, okay? But in truth, a mixture of two liquids, that would not be the case. Their vapor pressure would be lowered. You need a higher boiling point to do that. But interesting to see what they're going to accept there. All right, so again, I would think they would go, okay with that since colligative properties is not part of the curriculum, but gosh darn it, the boiling point's lower, intermolecular forces are weaker, therefore you're going to have higher vapor pressure with a compound with lower vapor, you're going to have higher vapor pressure with a compound with a lower boiling point. Okay, on to D. The mixture is heated to 198 in a sealed, rigid 12.5 liter. Now, if I look at 198, I can see that 198 is above both of these liquids' boiling points, so they're all going to become a gas. And guys, we got gases, we got what? A volume. Okay, we've got pressure. You should sniff this out. Yes, this is a PV equals nRT question. The only trick here is to make sure, and not really a trick, you must recognize that you need to be in Kelvin for your temperatures. The mistakes that people are making is they're trying to put the degrees Celsius into a gas law formula. And one way to prevent that is write the units in. I know you're under duress because of time, but the ideal gas law, some people pick the wrong ideal gas law. They've been using the one for joules, and you need the one with atmospheres, liters, mole kelvins. Write the units in, okay? If you write the units in, you can see which units we need. We need to have atmospheres. We need to have liters. So if you're in milliliters, you had to convert. Of course, we're solving for moles, and we need to have kelvins. And you can see everything is canceling except for 1 over mole, which is equal to mole. Use your units. That would have prevented you. Oh my gosh, I have to be in kelvins. And of course, you know, Celsius plus 273, Kelvin scale is the Celsius scale, started 273 degrees sooner. They give you, of course, both of these formulas. All right. So I believe that concludes, it definitely includes number 5. On to number 6. Number 6 is a galvanic cell, which is a battery. Luigi Galvani and Alessandro Volta, two people that were having an argument, and their argument led to the development of the first battery. So galvanic cell, voltaic cell, and you should recognize this to be a battery because of the salt bridge, and you should know this to be spontaneous. You should also recognize the fact that you're going to get positive volts for your electrochemical potential here, okay, or E0 cell. Okay, any case, back to this question, all right. What they want to know is write the half reaction for the oxidation that occurs. Okay, now they did give you a nice little hint here for 0.90 since you have positive volts. Okay, so they did give you that hint, but honestly, in a lot of these problems, if I know this is a battery and I'm looking to see who is oxidation or reduction, I need this to be equal to positive volts. Which one would I flip to give me? Remember, these are both written as standard reduction potentials. I don't know why they don't say that anymore. These are standard reduction potentials. Remember, the E0 cell is standard conditions. So they're always written as reductions, all your half reactions, just by convention. Convention means they've agreed upon it. So which one do we flip that's going to make this thing positive? Okay, well, it's going to be this one. And if we're going to flip it in the opposite direction, the sign is going to change. Okay, and therefore I know that the aluminum, when you add these together, is going to be the one, they're going to be the oxidation half reaction. But they also gave you another hint, okay? If we look, they gave you 0.90. Okay, so how would you, which one would you have to flip so that it would equal 0.90? Okay, and that being said, you could solve for aluminum. If you're not following me, you take the, if you take, I need these to equal 0.90 volts, okay? And again, if it's going to equal positive, which one do I have to go in the reverse? This is, remember, voltage is or E0 cell is a thermodynamic quantity. Thermodynamic quantity shows favorability in going in a certain direction. In this case, these guys are both negative. They don't like to reduce, so they like to oxidize. And again, all right, the only one that I can put together, and if you look, negative 0.76 plus a positive 1.66 volts gives you 0.9. But I didn't even need that hint when I looked at this. In fact, I just missed it when I first did it, because I just said, hey, which one do I flip to make positive? I also knew that aluminum was more reactive than zinc, and you know that too from these reduction potentials, because if you turn the reactions around, who's better at oxidizing? Well, who's got a greater oxidation potential when you consider them going in the reverse? It's aluminum. And why is that important? Because of this new mnemonic, anox, red cat, which means the anode is always the place of oxidation. Remember, electrodes are the place where the redox occurs. And this, of course, is the cathode, the place where reduction occurs. But in this battery, the aluminum is actually going to oxidize. All right, so I wrote the half reaction there for any reason that might have worked for you. I'm just giving you different ways to think about this. I've seen electrolytic cells, which are non-spontaneous. And which one do you flip so that you get negative volts? Because a negative volt means you require a power source. So again, even though we're seeing a voltaic cell, this could be the same kind of question if they gave you an electrolytic cell. What would be the difference in the diagram? They'd give you the power source. Okay, this is actually just a voltmeter here. All right. So that should be clear. And then write the balanced net ion equation. Well, if you know that the aluminum is going to oxidize, so I flip this, and then I write the zinc as such, all right, and I write the half reactions, I notice that I have 3 electrons that are being lost, okay, and 2 electrons, if you can just see that before I change that, or 2 electrons that are being absorbed. We have to balance them, so I multiplied by 2, distributed the 2 all the way through to get my 6 electrons. I distributed the 3. Why would I do that? Because I have a 2 and 3, common factor is 6, distribute the 3, and there's already 2 electrons. It gives me 6 and 3. The whole key for this multiplying through and distributing that number is to balance off my electrons. Okay, and I should never have any electrons in my overall reaction. And then just add everything together and then cross off anything that you need that's on both sides. In this case, it was just the electrons. So also do a quick check to make sure that the charge on both sides, 3 times plus 2 is plus 6. So this side's plus 6, of course, that's a standalone 0. And then 2 times plus 3 is plus 6. Both sides have the same charge. All right, so the overall net ion equation would have to have these coefficients and these ions. And it's a net ion. There's no anything else that had to be written or was written initially would be spectating. Obviously, they gave you net ion reactions to begin with. So that's it. Okay, so that's pretty straightforward. Put your half reactions together, balance your electrons by, if you have to, distributing, and then cancel your electrons or anything else to get your overall. Okay, so on to C here, which was a kind of a weird question for some. They said each electrode has a mass of 50 grams, sorry. The cell is allowed to run for a period of time and then stop. Which electrode's mass changed the most? Well, before we get to that, you should recognize this. Okay, let's get back on this, and I want to clean some of this up here. So we know that the aluminum is the anode. That's the place of oxidation. Based on the half reaction, you should recognize the fact that a piece of the aluminum is going to go by drawing it in. I'm saying it's disappearing as it becomes aluminum plus 3. So you should recognize that the solid, if we draw the half reaction up here, the aluminum 0, I'm just drawing the opposite of this reaction, is becoming aluminum plus 3, or 3 plus, and 3 electrons. So every time, and you should recognize, anytime you've got a metal that is neutral, 0, standalone, I like to say, it's a solid. And anytime you're making an ion, you're making it aqueous. So a solid is becoming an aqueous, so the solid is decreasing as it oxidizes. And what's happening in reverse is that the zinc plus 2 in solution is grabbing the electrons that are pumped from the anode to the cathode, and these electrons, let's say, build up there, and the zinc plus 2 is going to grab them, become zinc 0 right there. We're going to make a solid, so that's going to plate. So the question is, who's changing more? We know that aluminum is getting lighter because the solid is becoming an aqueous, and we know that the cathode is getting heavier because the aqueous ion is becoming a solid. So who's changing more? Are we going to increase in grams on the cathode side more than we're going to lose mass on the anode side? Well, they gave me an arbitrary value of 50 and they wanted to justify this with answers. So what I did, but you certainly could do this many different ways in my belief, I took the 50 grams and I basically make this statement to myself: if 50 grams of aluminum oxidizes, that means if all of the aluminum anode completely oxidizes, how many grams of zinc will be produced on the cathode? That's what I did. So it's a Stoich problem. That's all that is, based upon, and I used the overall balanced equation to do that. And I took my 50 grams and I made 27, converted to moles, used my ratios, and I should be canceling my units here. Aluminum is canceled, and once I have what moles of zinc, okay, I'm going to convert that to grams. And what I found was if I used up 50 grams of aluminum, if it completely oxidized into, guess what, its aqueous ion, okay, then I'm going to produce more grams of zinc for a couple of different reasons. There's 3 zincs being made for every 2 aluminums, and zinc is what? Has a higher molecular mass. So I just proved that there's a heck of a lot more addition of zinc that's going to plate on the cathode than the what? Aluminum is going to be oxidized, so zinc will change more. That's how I thought, and that's how I did that. I don't think you needed to use all of the 50, but you could have used any arbitrary amount. I just chose to use all that they gave me for the 50 if it all went. All right, but it definitely needed you definitely needed the overall reaction. You definitely needed to do the stoichiometry to figure out how many grams of zinc would be produced here. So I kind of like it. I kind of like the question. All right, so on to the next question. So number 6D, the final question here of the 6th question, 4-point question, and this one's tricky. This one is very slippery, I think. Not hard mathematically, but you had to watch what was going on here. So what they wanted to do in finishing up this electrochemical cell question, this voltaic cell question, they gave you other choices of chemicals with their standard reduction potentials, and they want you to come up with what combination would give you the maximum voltage. What they did say was they wanted you to use the zinc half cell. Okay, and so I know a lot of people, hey, we're going to keep the zinc as the cathode, and then we'll choose the beryllium to oxidize and go in the reverse, and we'll add the positive 1.5 to the negative 1.6, and that would definitely give you a greater voltage than the 0.9, but not the maximum. They didn't say you had to use the zinc, okay, the same way. They just said use the zinc half cell. So I'm going to make the zinc the anode, okay, and if I do that, I'm going to turn this around, this reaction around, and zinc is now going to oxidize and give me positive 0.6. That's why I have flipped the sign there. And then the interesting part is I'm going to use the gold to now reduce because it's got a very high reduction potential. So I don't know if people got, fell for the beryllium being the positive oxidation, but the best combination of chemicals would be the first 2. So when I put these guys together, or gals, depending upon what you want to call them. So I got the zinc oxidized 0.76, I got the gold reducing, and put that together, and I got 2.26 volts is the greatest voltage I can produce given all of these reduction potentials, assuming that I use zinc as one of the half cells. Now, if I can use any of that, use beryllium as the best, but since I had to use zinc, and zinc is best used at the anode, okay, it's definitely clear that these are the 2 chemicals I need here. So a little bit tricky for sure. I know a lot of people quickly put the beryllium for sure, but the best 2 chemicals, again, they had to use the zinc. They didn't say how to use the zinc, but the best 2 combinations would have to be the zinc oxidizing and the gold +3 reducing, as written here, to give you the greatest voltage. So yeah, I know a lot of people thought the zinc had to keep, still had to be a reduction. And when I originally read this, I thought that as well. And then I looked, whoa, wait a minute, they didn't say that. So again, a little slippery one here, but in any case, 2.26 maximum voltage you needed there. So on to the last question, number 7. Number 7, the final 4-point question of the FRQ. So here we go. So they gave us a Lewis diagram of the glycolate ion, and they want to circle the atom that accepts the proton. They're looking for the basic part of this ion. And the easy part to understand is, well, who's going to accept it? Well, we should know that bases, okay, are proton acceptors. And if you think about proton acceptors, I think about the idea that a proton brings with it no electrons, right? Hydrogen has 1 electron, so when it loses 1, it's a +1. So for it to be accepted, remember, hydrogen is in the first row or the first principal energy level, and it wants to be a lot like helium. The driving factor is to be like helium, which is 1s2, which has 2 electrons that fill the s orbital and thus the entire energy level. And that's a stable electron configuration. So where is hydrogen going to go? It's going to go where there's the most stable. And of course, the place it's going to go is a lone pair of electrons, because when it shows up with a lone pair, it's going to use both to create the bond. It's not providing. So we should also remember that a better definition of acid and bases, although not part of the course, is the Lewis, right? Bases are lone pair donators, but I know we're not supposed to go there, but it can help here to understand that the place this is going to go is a lone pair. Now, there's a couple different options. Okay, where would it go? Well, the options that have lone pairs to give the proton the most stability is right here, including the one that I circled as the answer. The problem with bringing the H plus here, it's going to make that a positive charge. So if I'm going to bring a proton with no electrons, it's going to make these oxygens positive. And certainly that could be the case. But the best place that accept it, and one that would attract it more, is the one with a formal charge of negative. So the H plus would go here. It could land here, but the place where it's going to accept it, most likely because of the -1 formal charge, okay, and again, formal charges aren't oxidation numbers, but we do know that this oxygen is negatively charged here. And if you think about it, okay, this is essentially a conjugate base. You've been learning acids and bases, so this needs one more H to bind here. And we've also learned, if you think about the reverse of this, is that you've got this carboxylic acid group, where we've learned in previous questions or theory that this H is acidic. It comes off because, well, these two O's are going to pull on this pair of electrons, and it's going to pull it this way and make the H come off, that electron drift that occurs. So we've learned all of that. So the point I'm trying to say is that, well, how does that acid get reformed? Okay, so again, the acidic H would be here, and when it's lost, okay, then that's going to be the basic part, okay, and that's where that's going to track the protons the best because of that negative charge there. All right, so in any case, that is going to be the basic part of that conjugate base that's going to absorb the protein and reform the acid. Remember, conjugate acid base pairs change by gaining an H or losing an H. So if that's the acidic H that belongs there, that's where the H is going to return, if that gives you another way to think about it. Okay, so in any case, 7 is where I circled. That is the basic oxygen, and if I put an H there, that would be the acidic H for reasons I just explained. So on to B. Let's be all we can be here. And now in this question, they want you to calculate the KB. Well, they gave me the KB equilibrium expression. How nice of them. And we are at equilibrium. Now, some people don't need the ICE table, but if you got this wrong, probably. So I wrote one, and this is the original concentration that they gave us, molarity. We have no hydroxide being made, or in this case, the conjugate acid being made. And because of the stoichiometry, we're going to lose X and we're going to add X because they're stoichiometrically 1 to 1. All right, and if you keep going, we know this is going to be 2.5 minus X, and then X plus 0 is X. You probably already knew that. So when you solve for this and you put these values into the equation, this being X and this being X, you get X squared, okay, over 2X minus X. Now, what they gave us is they gave us X. They gave us the molar solubility of the hydroxide. They gave us this, okay, which I have right here. And that's our X. So it's going to be X squared over the 2.5 minus X. Now, because the KB is so gosh darn tiny, the X is so tiny. Think about it. It's 0.00013. When you subtract it to 2.5, it's not going to change that significantly enough, so we can get rid of that and then solve for that. So it's 1.3 times 10 negative 5, which is your X squared over 2.5, and we get the KB, which is a tiny number. Tiny number, okay? I might have said this was the equilibrium constant, but that's how much hydroxide is actually coming off. Okay, any case, so that should have been straightforward. You've seen X squared over the original minus X thousands of times for weak bases, weak acids. Again, if you couldn't get there, the ICE table would help. And of course, you had to think about plugging your equilibrium values into this equation. They gave you the equilibrium value of one of the products, and because it's a 1-to-1 ratio, they're both the same. Any case, hope you realize that now if you got that wrong. All right, so on to C. C, they want you to calculate the value of Ka. We have Kb, and a formula you should know is Kb times Ka equals Kw. Nice little derivation is there for different places to find, but I don't want to go into that. So that's all that was. So if you've got the Kb that we just solved for, we have to know what Kw is, and you have this in your reference table. Kw, of course, is the equilibrium value for water dissociating into H3O plus and hydroxide, and that's 10 to the negative 14. So again, if you now see that, you just kind of plug and chug this through, and you get your Ka. And something you should recognize, if your Kb is really small, and you're timesing it by Ka, all right, the Ka is going to be bigger in relation to this number that stays constant. So you notice your Ka is much, much bigger than the Kb. Remember, stronger conjugate acid, weaker conjugate base. That's what this formula kind of tells us, right? Hopefully you learned that way. And then we have our last question. I'm going to mosey on down through that one. And this is the last question on the test. And it comes out of nowhere. I'm not sure how any of this fits in. I guess we have the glycosate or there's no glycolytic acid. If you put the H back on the glycolate ion, you have glycolytic acid. So there's some connection here. All right. Any case, so here's a mechanism. You should know from a mechanism that we're dealing with steps, elementary steps that lead to the overall reaction right here. And their student claims that the H3O plus is a catalyst. Now, a catalyst, we should understand, is something that we're going to add to some reactants, and it's going to change the pathway. A lot of times a catalyst is responsible for a certain mechanism. So if I zoom in here, okay, what did I add that created an intermediate that started a second step? Well, it's this guy. H3O plus. It created these steps because what it essentially did was it created an intermediate, which is a high energy reactive molecule that's now going to react vigorously. Okay, and so without this intermediate being produced, you don't have a second step, and what created the intermediate was the catalyst. Okay, now that's not always the best way to understand catalysts. The easiest way, especially if you're thinking about biology or biological catalysts, they can be used over and over. So the one way to also identify a catalyst, and I think probably the best way, is understand that catalysts are never consumed, which means they have to be reproduced. Okay, so we have our catalyst here, and later on in the steps, it's reproduced so that it can be used over and over and over again. All right, so you should know the difference between your intermediates, which do what? Link one step to the other, and a catalyst, which usually creates the steps. Okay, it doesn't have to, but what is best is that it's never consumed, which means it's going to be on a reactant side and be reproduced so that it can be used over and over and over again. So I kind of say that here. I agree. And again, here comes with the agree or disagree kind of question. And I said agree. Make sure that you answer that the H3O plus, the hydronium ion, is a catalyst because it is introduced as a reactant in step 1 and is produced in step 2. That to me is important to say those things so that you don't misinterpret that to be an intermediate, which is produced in a step, but then it's a reactant in the subsequent step because intermediate's linked. And to me, what makes this a winning answer, okay, we all want to win, is catalysts are never consumed in a reaction. Okay, that's important to recognize that they're reproduced. All right, so I hope this helped in a big way. Good luck on your test if you're using this for a future test, and I hope this made sense for the test that you just took.